YouTube. All right, so thanks everyone. Thanks for coming back, and let's continue with the talk by Lisa Hartung on log-correlated fields, some useful tools. Lisa, would you like to continue? Thanks everyone. Thanks for coming back, and let's continue with the talk by Lisa Hartung on log-correlated fields, some useful tools.
Okay. Somehow I hear the live stream, the delayed live stream. I think.
Yeah, I think it's fine now.
Okay, perfect. Yeah. Okay, so yesterday we saw. Let me just quickly go back to the notes from yesterday. So yesterday, we convinced ourselves that if we look at the binary branching random walk with Gaussian increments, the maximum should not be larger than this. And in fact, I hinted at the end that actually this is not the answer that this somehow is not the correct answer. Namely, that the correct answer should be this one. So the order of the maximum should be square root 2 log 2n minus 3 over 2 square root 2 log 2 log n. And what I would like to do now is I would like to explain to you why we see this 3 over here. And so why is there 3? So in fact, we should not only take into account the number of particles and the variance that they have, but we should, we look at the binary branching random walk with Gaussian increments. We see this, right? What we should kind of take into account is that this is a process that somehow level for level, this maximum evolves. Right? So we should maybe more imagine it like a cone. And if we look at a level k, we have 2 to the k random 2 to the k leaves, right? And all of them are Gaussian with variance k. And so at level k, the maximal particle or the maximal value should not be larger than what we expect to be the maximum of 2 to the k Gaussians, right? Because we learned yesterday that somehow the maximum at time n, right? We can somehow bound the probability that this is large by the corresponding quantity in the independent setup. So somehow the maximum value at time k, right, we have 2 to the k Gaussian, should not be larger than roughly square root 2 log 2, that's just the constant that we got yesterday, times k, right? And this is true, and so this is not true for all. So this is true for all levels k. So, of course, now I have to be slightly careful, right? Because I have n levels. So, right, if I now imagine that I build up this branching random walk level by level, right? I need to take into account that if I view this at this point, you know, as an evolving process somehow, right? I have to control the maximum at every level. Right? So this is true for all k. K is somehow between 1 and n. But n, right? But n, that's just a linear thing. I mean, n is obviously just a linear function in n, and the probability that the maximum was large, well, for this we use Gaussian tails, right? So somehow the cost that at level k I see something that's much larger than the typical maximum should decay in an exponential fashion because I use this Gaussian. So in fact, I can turn this rough argument that at one specific level k, the maximum shouldn't be larger than the square root 2 log 2k. I can turn this rigorously into the following. I can turn this into, with high probability, there is no and now I will really use the term particle. Which is above the function, and now I view it as a function in time that maps k to this linear function square root 2 log 2 times k. And now, well, because we have this n points where we want to control it essentially, well, we will just add some large constant log k minimum n minus k and well, we also, because this somehow becomes small, so this k minimum n minus k becomes small when we are close to n or close to 0. Maybe we just want to say this for k. We just this way, right? We want to take this function and then we take the maximum with some cost. Let me just write it this way. Right? Otherwise, we could also say that we only want to look at some generation at k that is between some r and n minus r. But let me just write it this way. So what do I mean by particle? Well, we look at the value, right, at some leaf here. And now if I look at this, right, I have this xv of n, right? Of course, there's this path, right? Of course, this leaf somehow came there. So there's this path to the root, right? And of course, now I can look at xv of k to just be the sum of the weights up to generation k, up to level k, to be consistent. Right? And now I can somehow view this collection x. Now I can, for one v, I can really look at this collection x v of k as for k in 1 to n, right? This is really a path or a random walk with Gaussian increments. And, right, so, and, right, this idea that at the previous level, the maximum, so at this previous level K, the maximum should not be too high. Well, this means this is exactly a constraint on this value xv of K, right? So roughly speaking, what we want to say is, well, we've learned that at a time K, my maximum shouldn't be larger than this. Now I give myself a little bit of wiggle room and I say, well, I want this to be kind of true at all levels simultaneously. So I need to maybe increase it a little bit. But once I do this, right, I actually believe that if I look at this branching and walk, so let me draw this picture again. Then what I can find is, well, now let us see this really as a picture in space. So we expect the highest particle to be at roughly square root 2 log 2 times n. Right? For now, let's forget about this log term. Right? And we have just learned that roughly speaking, also at each time k, right, the maximum should not be much higher than the linear function that connects 0 to square root 2 log 2n. In other words, so I give myself a little bit of space over this linear curve, right? And I just say, and what we just learned just says, okay, so with high probability, there is no particle in this region. And for convenience, right, because we will not, so for convenience, right, you might just pretend that this region is just really everything above this point. But this tells us something, right? Because imagine, right? So now we are going to imagine you have a particle, or you have a value, right, at time n. So one of your random walks at time n reaches roughly to first order in some sense, square root 2 log 2 times n. So this means we actually find someone sitting over here. Right? But now I've just tried to kill this. But now, right, we also know there's a path leading there. So then this means, right, so this particle, let me just this way. So to this particle, we can find a path. Actually, there is so to this yellow particle, there is a random walk path from 0 to this location. That never enters the forbidden region. So if I draw this path, right, it has to do something and reach this point. And it's not allowed to go to the red region. But of course, right, now I can flip, right? I can draw this picture slightly differently. So what I'm doing is I just take 0, fix it, and I take this final point go to log to n, and I turn this picture to take out the linear drift. Right, so in practice, so I keep my 0 here, and I just turn it such that at time n here, I am also at 0. And of course, then I also need to correspondingly turn my yellow line. And I'm also turning my forbidden region. So what do I have now? Well, I turned this, right? I just turned the picture. I didn't really change any probabilities. But now what I see is, well, actually the random walk leading to the maximum, leading to this maximal particle, or the particle close to the maximum one, is actually a Gaussian random walk that is essentially, that is more or less forbidden to be positive, right? Because this line that now connects 0 and 0, it's just always 0. So essentially, this forbidden region, right, is everything where it's positive. So what I see is, well, if there's this forbidden region, then actually the path of this maximal particle, right, needs to look like a Gaussian random walk. And of course now in this picture, right, I have told this guy where to end. So essentially what this is a discrete time Brownian bridge. From 0 to 0 in time n. But of course now, if I just have a usual Brownian, right? But actually the probability, and the probability that if I look at such a discrete time Brownian bridge, that goes from 0 to 0 in time t, in time n, right? I mean, this object that this wants to stay below 0, essentially, apart from, and now we have to formally exclude apart from the very beginning and very end. So let me just write stay below 0 we just say below 0 away from the endpoints. Maybe. Because maybe at the endpoints we want to give things a little bit of space and not worry. I mean, here we are also in discrete time, so we can also just say that it always stays below 0. Right, but of course at the very end and very beginning I'm somewhere, so let's just this. Well, this is something that is actually known, right? So this is not something that is of order 1, because typically, if I look at a Brownian bridge, right? Essentially, it's a Brownian bridge. You want to fluctuate, and it has variance n. You want to fluctuate like square root of n, right? So typically, this object would like to fluctuate like square root of n, right? And if I'm asking it to actually, so usually I would be doing something like this, where things should be of order square root of n, but now I'm forbidding it, right? And so this actually is not of order 1, but this is roughly of order 1 over n. These type of estimates also for random walks are referred to as parallel estimates. I mean, and so what do we see? Well, in fact, this path of the maximal particle is not a typical path, right? That we would see if we would just look at, let's say, 2 to the n independent Gaussian random walks, because they would actually, if we would look at the maximum object there and we wouldn't put a constraint, actually it would just look like a typical Brownian bridge, right? Discrete time Brownian bridge. It would fluctuate like square root of n, and I wouldn't have to pay anything. But actually here I have to pay something, because the good path is one that stays below 0. But now let us try to put this back. So let us try to combine this. With our upper bound from yesterday. Right, so yesterday we were just looking at the probability that the maximum over all values at n is larger than essentially square root 2 log 2 n. And now let me just write the correct answer here. So let me just put 3 over 2 square root 2 log 2 in here. And well, we will add some 1, which I will just, let me just call it y. So this is what we believe is the true answer. Ah, well, I forgot the logarithm. Log n. And now what I will just say is that, well, I will just add in this probability the additional constraint. I will just say Right, I will look at this event intersected with the event that there is no particle. So there's no particle or no path in the forbidden region. And now this looks like a complicated probability, but in fact, if we use, right? So if we use this a priori information that I've just put in, that we are not too high at previous levels, well, if we actually write this again in terms of our counting particles, so k goes from 1, no, I shouldn't use k because I already used it. So L goes from 1. Let's just see. Let's just stick to the notation from yesterday. V is in the n indicator function. And now I say, well, xv of n should be larger. And let me now give this object a name. We call this m of n plus y. And we want xv at previous levels. And now I will just, I will be sloppy here. Right? Because I don't really want to worry about all these log stuff and so on. I will just say this should be smaller than square root 2 log 2. So I'm just simplifying my wide region a little bit. And now, well, I want the probability that this is larger than 1. Right? Because I essentially just say, well, right, I know that there's no particle in this forbidden region. So in particular, the maximal particle should be one that does not enter the forbidden region. And so I should find a particle that goes high enough and that stays out of the forbidden region. And now I can use my trick from yesterday again with Markov's inequality. So I can bound this by the expected value of the sum. E in the n, and here I just copy. But now I can also say, well, again, this object only depends on one path. So this is nothing but 2 to the n times the probability that xv of n is larger than mn plus y, and 3k is smaller than square root 2 log 2 . Right? And now, so now essentially what I've done is I've fixed the endpoint of the path to be this or something above, and I've given it this construct. And now, right, I can use that, and now I can transform this, right? Because I can use, so I can essentially take out, so I can take out the drift here. So so what I want to do is I want to take out the linear drift. And well, one way want to do this is that you replace this xv of k. You split this, you look at c of k, and then you divide this by k. You subtract k over n, xv of n. This is now a discrete time Brownian bridge. And in particular, a discrete time Brownian bridge is independent of the endpoint. And so what I can now do, I can rewrite this. And now I can use that this term here in the back, right? This is essentially k over n times, because now I have xv of n larger mn, square root 2 log 2 n in first order. So we see that if I do this transformation here, right, the object that I need to consider that becomes the Brownian bridge is xv of k minus square root 2 times k. So essentially, that's this part here. And then I have a condition that the endpoint needs to be larger. So if I do this, I get 2 to the n. Now I use the independence of the x endpoint. V of n is larger mn plus y times the probability that this discrete time Brownian bridge, and now I have to, I will only say approximately because I have been not too careful about this beginning and end and the precise region, k over n v of n being smaller than 0. Okay, so this is, so the last part is the probability of a discrete time Brownian bridge to be smaller than 0. And now these terms, well, this is 2 to the n. The second one is just Gaussian. So this one we already know how to take care of it. It's square root of n divided by mn plus y e to the minus mn plus y squared over 2n. That's exactly the same computation as yesterday. And then I have this Brownian bridge term, and this Brownian bridge term gives me an additional 1 over n. Right? And I've not taken care of the constants because I have already been imprecise in this respect. Okay. So what we see now is that actually I have an additional 1 over n. And now if we recall from yesterday, so yesterday, we saw that we had to create a logarithmic term in the order of the maximum to kill this prefactor. This prefactor over here, right? This over here is roughly 1 over square root of n. So we needed 1 over 2 square root 2 log n with a minus to get rid of so to cancel the 1 over square root n. Now, because we have used information on the paths of our branching random walk, we have an extra 1 over n. So this extra 1 over n, right, is of course nothing else but 1 over square root n squared. So now I have 2 more to cancel, 2 more square root of n's to cancel. So now we need this. We need 2 more of these terms, so we need 3 of them in total. 1 for the 1 over square root of n that we already had yesterday, and 2 more for this extra 1 over n. And this is actually the true answer. So this is the correct answer for the order of the maximum. And of course, this you can turn into, and this gives you essentially a more or less rigorous proof of the upper bound. So this gives the upper bound. For the lower bound, which I will not do in detail, for the lower bound, what you can use, what people usually use is the second moment. So if you have, because if you have this probability that z is greater or equal, you have this object which is a sum of v in Vn. You have these indicator functions, and now you ask your particles to do whatever they want, whatever you want to count. And you say this is greater or equal to 1. Now you can lower bound this by using Cauchy-Schwarz inequality, or it's also called Pauli-Sigmund. You can lower bound this by the expected value of the sum v in Vn of this indicator function. And now you square it. And what you need to divide by is the expected value of the sum v in Vn squared. Now this would start with ugly. And so this gives you something meaningful. So this is useful. Essentially, when you know that this term on the left-hand side is something that is of order 1, right? I mean, if what's on the left-hand side just says 0, then it's not a particularly interesting lower bound for probability. Right? But if it's something that's of order 1, right, or that you can make close to 1, then this is useful. And so what people try to reach in this localization, so in some sense, often the goal is to put an extra constraint in this indicator function, of the particles that we want to count, right? Such as the paths do not go too high, right? But in principle, you can put whatever you want to put there, such that the second moment of the sum, so the expected value of V, right? V and V prime are in the end indicator function for V times the indicator function for V prime. Is of order of the expected value squared. So in this particular example, so here, so we used this extra information on the forbidden region. But somehow this is something you can play around with. So if you have a slightly different, process that you would want to look into, right? The question always is, can I do something similar? Can I try to understand how a typical particle doing whatever I'm analyzing is doing? Can I formulate it in such a way that I can put it in as an extra condition in this indicator, so that I say that I only count good ones, good particles. And actually very often this can be an iterative process, right? So actually finding good extra conditions to put in this indicator function can be tricky. And sometimes you can do it in several steps. What do I mean with several steps? Well, if you believe me, what I've already told, if you believe me, what I've told you, right? We now know, so we know, let me just give you an example for this. So if we know the order of the maximum of the branching random walk, let's assume we know this, is this M of n. Well, now I can just add this as a constant. Now I can, in principle, add this event that the maximum of my branching random walk is below mn plus some very big constant. Because I know this is true with high probability, I can in principle add this to the indicator function. To find out more. right? Of course, then maybe I will not ask what's the probability that the maximum is so high, because I already know that. But if you recall, right, we were also interested in describing. We were also interested in describing so this might help you to describe the other high values. And in which sense, and I will not do this I will not do this in super great detail, but I will do it with a picture, right? Because now, right, I can imagine, so I have my 0 here, and I have this one from before. And I will now just draw the upper part. I have my maximal particle sitting somewhere here. And I also know now, well, I know that this path. So this is this Brownian bridge path going to the largest one. Right? And now in principle, right, I can describe the process seen from this maximal particle. Namely, I can say, well, there's this highest particle. Along this path, at each generation, I have a new tree, a new branching random walk. I have kind of a new branching random walk attached. Right? Because if I split into 2, I always split into the one that's going to be the maximal one, and then I have one other one that splits up. And these are all these different branching random walks. And this picture is now a bit misleading because, of course, they all overlap. Right? So I have this line, I have this path to the maximum. Plus, I have this collection of smaller branching random walks that branch off from this path. And actually, what turns out to be useful is to say, well, now this maximal path, well, so now this maximal, so the maximum of these attached branching random walks, well, I know something about it, right? So of course, if I've drawn this picture already seen from the maximum, I know that they are not going to go above this maximal value. But even if I would just have picked something that's close up there, right? I could always have said that these maxima of this attached branching random walks plus their starting point, so plus the value where they branch off from this yellow path, well, this needs to be smaller than the maximum, the total maximum. And it actually turns out if you use, right? It actually turns out that in that case, it's actually useful to somehow work directly with these type of localizations. And this actually, I mean, I will not really do this, but actually, if you do this, right, what you can obtain, if you use this type of machine, you can obtain you can use this actually very nicely to obtain quantitative estimates. On the level sets of high particles. So this is something that's done, that we do in a paper with Azea Martinez and Oren Louisdor. And it's written for branching random motion, but there's not that much of a difference to branching random walking. It's really just the continuous time analog. Right? So even if localization at first, this path stuff at first seems maybe a little bit, somehow not very fine, but a very brutal tool, it's very useful, and you can refine it somehow. If you learn more about your process, you can always add this back into the picture and try to redo a very similar type of computation, but more precisely. Right? And what I should also add, maybe, so what I should also add, so if you try to find this extra condition and how you should match it, there's actually, so there's a very nice article. There's actually a very nice, this, so this is more on this first and second moment method. There's a very nice kind of overview article by Nicola Kistler. And well, it has a slightly complicated title. I will add this to the notes later because I don't want to warn me, but somehow there this how to find proper things to put and proper scales and so on is very nicely explained. Right, and of course here I've explained to you somehow the model where I have used this branching random walk, where this path is completely explicit, right? So in other models, e.g. in what I called yesterday example 4 and example 5, which were the Riemann-Zeta function and this random matrix theory thing, right? Well, you first need to actually, right? You have other difficulties, right? Because the first step is you need to find a good analog, a good notion, usually of what you mean actually by the path, right? So if you have a random walk, it's kind of clear what it is, right? It's in branching random walk, it's there. In VVM, it's there. But in the other models, you actually have to look for it, right? So the first step somehow, if you want to use this method, is always to somehow find what represents this yellow path, and this is sometimes also referred to as the good scales. Right, and sometimes that's more apparent than in other cases, and often this can be done, for instance, by sometimes this can be done by comparing covariances, or sometimes it's block and summons and so on. But this is somehow the first, challenge. And then, of course, right, a second challenge that you have is that, well, I did not say much about computing the second moment, but you can imagine what you need. So let me just quickly go back there. Right? So if you were to compute this second moment, right, what you have essentially here is the probability that x of one leaf and x of another leaf do something, right? So this actually involves two. So this actually involves two paths, because I have this path that leads me to xv of n, and they have this path that leads me to xv prime of n. And as I told you yesterday, well, branching when a walk is super nice because you have this one particular point where the path before is completely correlated. And after this one particular point, well, they branch off from each other, they take different increments. So afterwards, they are independent, right? And now, if you want to compute the probability that this value does something and this path does something, and you want to compute that this does something and this path does something, well, you can essentially, you only have one event until they branch, and then what they do is independent, right? So you can do you can compute these things rather precisely because of this. But of course, in other models, right, all these things are only approximately true, right? So in other models, right, you have to actually think about how to compute the second moment. Right? Even if it's just a second moment, it's not always completely clear what is the smartest way to do this. And so, and there are ways to do these things, and one way, so one option sometimes, it doesn't only work, is you can try to compare your model to a corresponding, or to a branching when a walk where you of course match where you somehow have to match the number of levels that you look at, right? So that it fits. And then you can try, right? And now the question, of course, is, well, compare sounds nice, right? Because we know all these models have a covariance structure that you can kind of map from one to the other, because they all, because I started this mini course by saying all log-correlated fields are log-correlated. But of course, the question of how to do this comparison is not so easy. And essentially, that will be something I will be focusing on tomorrow, is, right? So one option is to use something that's called Gaussian comparison. And in some other cases, well, it's also essentially when you're Gaussian, in some other cases, you might also want to do it slightly differently. It's, for instance, what's used a lot in the Riemann zeta type models is to look for various scene bounds, because they are sometimes very, very, very nicely to be applied there, right? And of course, you also can try to do this comparison. I mean, this is somehow for a very direct comparison with branching when a walk. Of course, you can also try to do it more roughly and only have the branching when a walk in your head. But this will be somehow, so these will be two things that I will be focusing on tomorrow. Not tomorrow. It's actually 1 because it's Thursday. And I will stop here for today, right? So what you should take home from this second hour somehow is, well, the 3 is there because the path of the maximal particle looks like a Brownian bridge that is conditioned to stay below 0, and this costs you a certain probability, and then you can do the computation, and the answer is 3. And the second thing you should keep in mind is that actually this is that, well, upper bounds work with Markov's inequality, and lower bounds really like to use this Cauchy-Schwarz inequality. Or Pauli-Sigmund inequality. And this is actually a very useful inequality because it's rather basic, and but it's true and useful. And you should keep in mind that sometimes finding this localization that we have seen is actually not that easy, right? It's something you need to work for, and sometimes it's actually useful to do it in steps. To first do something rough, and then you do it. Okay. So I will stop here, and thank you for your attention. And I'm happy to answer questions if there are some.